Hey, so welcome to the review session for the test 5 for the full semester of statistics. This is covering chapters 7 and 9. My name is Maxine. I work at the Academic Support Center. Um, we are recording this, and I'll be sending a link to this recording to everybody who's provided their email address. You can email me directly. I've put my email in the chat, which I will pull back up here. Or you can type your email in the chat. All right, so for chapter 7, we are talking about hypothesis testing. So there are a few things that we're going to be referring back to over and over. So I took just like a super quick picture of in the physical textbook of a couple of these things since we're going to be referring back to them. I would recommend if you have some sort of study sheet or summary sheet that you're creating, that you put these rules or charts or whatever onto that sheet. So I will pull those pictures out as we get to them. But let's go ahead and dive in. I'm going to go ahead and zoom this in just a little bit more for these problems where we do have a little bit more space on the page here. That's a little bit lighter. Okay. Hopefully that's not too small to read. Okay, so number 1, a brewery claims that the mean amount of beer in their bottles is at least 12 ounces. Determine whether the hypothesis test for this claim is left-tailed, right-tailed, or two-tailed. Okay, so the first thing we want to do is we want to write what is our claim. Let me admit. Hi there, Christina and Alexa. So just a heads up, we are recording this. I'll be sending links out to the recording, after it's done, but I just always have to make that announcement that this is being recorded. Well, you haven't missed anything. We've barely even started, so. All right, so number 1, brewery claims the mean amount of beer in their bottles is at least 12 ounces. Determine whether the hypothesis test for this claim is left-tailed, right-tailed, or two-tailed. So the first thing that we do is we say, what is our claim in symbols? Okay, so they're talking about a mean amount. So the population mean. And what they've said is that it's at least 12 ounces. So at least means greater than or equal to. Okay, now in your book, let me get the page out here. There is a handy little chart. If you're not feeling super confident with taking those English phrases and translating them into, what means less than, what means greater than or equal to, all that kind of stuff, they have provided a whole bunch of examples in the book. So you can certainly, I'm going to have to zoom this back out. There's not room to put the book up here. All right, we're going to zoom out for just a second here so I can put the book here. So they have this chart here, right? So phrases like greater than or equal to, at least, not less than, not shorter than, right? So that's going to be your null hypothesis. Those are all things that mean greater than or equal to. Okay, so if you find that you're having trouble just translating those English phrases to what the corresponding symbol should be, then refer back to the table in your online textbook. Okay, all right, so for this one, down over there, let's zoom back in here. All right, so okay, we have our claim. We said that our claim was that the mean is greater than or equal to 12, right? At least 12, greater than or equal to 12. So now what we need to do is we need to say, okay, well, which of those is my null hypothesis and which of those is my alternative hypothesis? Okay, so that is your null hypothesis. So an H sub 0, an H sub A. You can write the A like that, or you can, might be easier to write the A like that so that it's a little easier to see that there's a little tail there. But that is your alternative hypothesis, right? So scooch this over here so I can see the whole page. All right, so your null hypothesis is always going to have some type of equality in it, okay? So it's going to have symbols like equal to, or greater than or equal to, or less than or equal to. Whereas your alternative hypothesis is never going to have any sort of equality. So the corresponding null hypothesis to each of those, I'm sorry, the corresponding alternative hypothesis to each of those null hypotheses is going to be not equal to, less than, and greater than. Okay? So you're going to have to make sure that you know that. Null hypothesis has to have some sort of equality. Alternative hypothesis does not have any type of equality. It's all inequalities. And you'll need to know that if one of them is, well, if your null is equal, your alternative is not equal. If your null is greater than or equal to, your alternative is less than. If your null is less than or equal to, your alternative is greater than. Okay, each of these corresponds this way. Okay, so we determined what our claim was. So now we need to determine, okay, well, the thing that we have, our claim, did that give us the null hypothesis, or did that give us the alternative hypothesis? Sometimes the claim that they give you is one, sometimes it's the other. It'll be different for every problem. So we look to the symbol and we say, what symbol do we have here? Does this symbol have some type of equality? Yes, it does. So what they gave us in this particular case was the null hypothesis. Okay. So once you fill in whichever one of these is your null hypothesis, you're going to write out your other, or sorry, whichever one of these is your claim, you're going to fill in your other hypothesis. So you're just going to write your same symbol, and you're going to write the corresponding symbol that is the complement. So this is the complement of this, this is the complement of this, so on and so forth. So the complement of greater than or equal to is less than. Okay. All right, so once you have both your null hypothesis and your alternative hypothesis, you're going to draw out what type of tail situation you have going on, okay? And it's always based on your alternative hypothesis, okay? So whether you're left-tailed, right-tailed, or two-tailed is always based on your alternative hypothesis, regardless of what your claim was. Whether your claim was the null or the alternative, it doesn't matter. The alternative hypothesis was what we always look to see if we're right-tailed, left-tailed, or two-tailed, okay? All right, so what are those tail situations? Okay, if we are less than something, then that is a left-tailed. Left-tailed less than. If we are, which by the way is what this is, right? But just to show you the other examples, if something was greater than, we would have a right-tailed hypothesis. And if something was not equal to, we would have a two-tailed hypothesis. So left tail, right tail, two tail. Okay. So you'll want to make sure that you've got that down pat. Okay. Because you're going to be doing that for every single problem, which you've probably already figured out by now, because hopefully you've done all the homework and you're just doing the test review assignment. Okay. So number 2, what are, let's see if we can zoom in some more again. I feel like it's kind of blurry, but all right, what are the 2 types of hypotheses used in a hypothesis test, and how are they related? So we kind of just talked about that, didn't we? We just answered this. The null hypothesis, so H sub 0, and the alternative hypothesis. Okay. And how are they related? They are complements, right? So if one of them is greater than or equal, then the other one has to be less than, because those are complements of each other, which is what we had before, right? So remember, complements together, they cover everything. They cover the whole situation. So things that are greater than or equal to 12 and things that are less than 12. Well, that covers everything. All right. Describe the two types of, actually get this down so we can see it. Okay, describe the two types of errors possible in a hypothesis test decision. Okay, so for this one, let me pull the book back up here. We've got, to the right page here, they've got a lovely chart like they do in so many of these. I had it open and then the book closed, so now I have to go back to that page about the different types of errors. Okay, and I gotta zoom this out. Okay, so we have a type 1 error occurs if the null hypothesis is rejected when it's actually true, and a type 2 error occurs if the null hypothesis is not rejected when it's false. So it should have been rejected, but it wasn't. Okay, so I like that they give you these types of tables where they say, okay, well, is your null hypothesis true or false? And then what did you do? So if it's true and you don't correct it, then that was the correct decision. But if it's true and you did reject it, that was a type 1 error. So if your null hypothesis was false and you rejected it, then that was the right thing to do. But if it was false and you didn't reject it, that's a type 2 error. And the example that they give that I really like on this next page here is, oops, is if somebody is innocent and they're found not guilty, that's justice. But, sorry, I can't hold my pencil that way. But if they're innocent and they're found guilty, that's a type 1 error. Okay. If somebody is guilty and they're found guilty, that's justice. But if somebody is guilty and they're found not guilty, that's a type 2 error. And they talk about how a type 1 error is worse than a type 2 error when we talk about the justice system, right? Like we don't want to send innocent people away to prison. Okay, so knowing the, gosh, this Zoom is going to kill me. All right, so knowing what we do with our chart about the different types of errors. So a type 1 error occurs if the null hypothesis is rejected when it's actually true. And a type 2 error occurs when the null hypothesis is not rejected when it's actually false. Okay, let's see if I can put this down so that it won't lose my page again. All right, there we go. So that might be, I didn't print that one out, but that might be another one that you jot down or print out for your study sheet. Okay. All right. So number 4, use the given statement, zoom in a bit more here, to represent a claim, write its complement, and state which is the null and which is the alternative. Okay, so they're saying you've been given this and you're being told that this is the claim, that P is less than 0.34. Okay, so now we need to find the complement. So we're going to go through the same type of thing that we did in the first problem. So this was our claim. We need to determine what is the null and what is the alternative. So the null always has to have some kind of equality. The corresponding alternative cannot have an equality. So the claim that we were provided has a less than symbol. So that means it's going to go down here. It's going to be our alternative hypothesis. So that's our claim. In this case, our claim is the alternative. Okay, so we've written down the alternative. Now we're going to write its complement, the null. So we had a less than symbol. So the complement of that is a greater than or equal to symbol. And you keep your number the same. That's a 3. Sometimes my 3s look like 5s, but that's a 3. Okay. Okay, so now they want us to fill it in a particular way. Okay, find the complement. Okay, we did. The complement was that P is greater than or equal to 0.34, greater than or equal to. So there's greater than or equal to. And they want us to make sure that we've identified which is the null and which is the alternative. So the null is greater than or equal to, and the alternative is less than. Okay. So hopefully you guys are feeling okay with this part of the process because you're going to be doing it a million times. Okay. So number 5, given the null hypothesis of the mean is greater than or equal to 18 and a p-value, now here they're just using a capital P, but I like to write out p-value. But if you just see the capital P, that's your p-value. So our p-value is 0.067, and they want to know, do you reject or fail to reject the null hypothesis at the 0.05 level of significance? Okay, so we have to remember what our rule is for using a p-value to make a decision. So this is one of the ones that I printed out that I was talking about at the beginning. So I just like literally took a picture of the textbook on my phone and just printed it. So we're going to keep coming back to this because this is going to be, so there's several different ways of doing hypothesis testing, right? But this is generally the easiest because you just plug it into your calculator and it gives you your p-value, okay? Now we can calculate the p-value. It's a multi-step process to do that. We have to find our standardized test statistic, and then we use that to find our p-value. But once we have our p-value, we're using the p-value and we're comparing it to the alpha, which is the level of significance, right? So our level of significance, our alpha for this particular problem, is 0.05. So we need to compare this p-value of, so p-value is 0.067, and we need to say, okay, is my p-value less than or equal to my alpha, or is it greater than my alpha? So this p-value compared to this alpha, the p-value is greater than this. It's greater than alpha. So we are going to fail to reject the null hypothesis. Okay. So like I said, I'm going to keep pulling this sheet of paper out because we're going to keep looking back at this. When do we reject the null? When do we fail to reject the null? Okay. So in this case, we failed to reject because our p-value is greater than our alpha. Okay. Okay. You wish to test the claim that the mean is less than or equal to 29 at a level of significance of 0.01 and are given the sample statistics n or sample size of 40, and x bar or sample mean of 30.8. Assume the population standard deviation, or sigma, is 4.3. Compute the value of the standardized test statistic and round your answer to 2 decimal places. Okay, so we are going to calculate the standardized test statistic, but we're also going to be kind of writing everything out because you want to get in the habit of kind of going through the problem from beginning to end. Okay. All right. So the first thing that we're going to write out is our, let's see, do I have room over here? Yeah, is our claim. Okay. So the claim they gave us was that the mean is less than or equal to 29. Okay. So now we need to say, is that my null hypothesis or is that my alternative hypothesis? Since it has some type of equality and not just an inequality, that makes it the null hypothesis. So our null hypothesis is that the mean, the population mean, is less than or equal to 29. Right, that's our claim. And so now we need to write our alternative hypothesis, which is the complement of that, which is that the mean is greater than 29. Okay. Now we're going to use our alternative hypothesis to draw a picture of what we have going on here. This is greater than 29, so greater than is a right-tailed test. Okay, so when they ask for the standardized test statistic, test statistic, they're asking for the z-score that separates this shaded area from the rest. And this shaded area, the area of the shaded region, is your p-value. Okay. All right, now they're not asking us to find the p-value. They're just asking us to do part of the work, to find the standardized test statistic. So we're going to do it 2 ways. We're going to do it by hand, and then we're going to do it in the calculator. So let's go ahead and write down everything that they gave us. So I always like to write my level of significance kind of right up at the top near my hypotheses, is 0.01. Okay, and then they give us a bunch of other stuff. So they give us that the sample size is 40. They give us that our sample mean is 30.8. And they give us that our population standard deviation is 4.3. Okay, so first, let's go ahead and do this by hand. Okay, so to do this by hand, we're going to use the formula. So the formula for the, I guess we'll do it over here, the z-score that is your standardized test statistic is, write this out. So it's your sample mean minus your population mean all over population standard deviation divided by the square root of your sample size. Okay, so if you're doing it by hand, this is what you're doing. Okay, so let's plug in what we have here. We have 30.8 minus 29, and that's all over 4.3 divided by the square root of 40. Now, when you go to plug this into your calculator, I would always suggest putting your numerator and your denominator each in parentheses, right? That's going to make life a little bit easier for you. So put this up here. So we're going to do 30.8 minus 29 divided by 4.3 over the square root of 40. And I'm getting this 2.647488274. And they told us to round to 2 decimal places. And I always take a second to remind everybody of how to round, because you never want to get a problem wrong after doing all that work just because you forgot how to round, to 2 decimal places. So I'm going to underline the number that I'm going to round to. You look to the number to the right, If that number is 5 or more, your underlined number goes up 1. If that number is not 5 or more, your underlined number stays the same. It is 5 or more, so the 4 turns into a 5. So that's how we get the 2.65. Okay, so that is how we do it if we're going to do it by hand, right? Which you need to know how to do, right? You need to know that there's a formula and that you can do that. However, as with so many other things in this class, part of the class is learning how to use the tools that you have at your disposal. And one of those tools is your calculator. So in order to find that by hand, what you're going to do is, actually, should I write that? Well, let's do it and then I'll write it out. You're going to go to Stat. You can't see that. I'm going to zoom out a little bit more. You're going to go to Stat button, which is right here. You're going to arrow over to the right to Tests. So arrow and arrow. And then this first one right here, the z-test. So like with so many things in this class, the way that you do it is kind of separated into 3 different distinct situations. One is, do I have a population standard deviation? 2 is, what if I don't have a population standard deviation and I only have a sample standard deviation? And 3 is, what if I'm dealing with a proportion? So for the first situation, you use a z-score. For the second situation, you use a t-score. And for the third situation, you are using a z-score, but it's proportions, so you often have slightly different formulas. So what we had going on here in this problem was we did have a population standard deviation. So we're going to use this first one right here, number 1, z-test. Okay, so you're on z-test. I don't want that reflection right there. You're going to make sure that stats is selected, not data, and you're going to go through and you're going to plug things in. Now, this first one here is the number that you use in your null hypothesis. Okay, so in our null hypothesis, we used the number 29. Right, then it wants our population standard deviation, that was 4.3. Then it wants our sample mean, that was 30.8. Then it wants our sample size, that was 40. Okay, and then what it wants is our alternative hypothesis. And you'll notice that the symbols that we have here are only the symbols that are used in the alternative hypothesis. So if you forget and you're like, oh, am I supposed to be using null or alternative for these? You'll be able to tell if you just go ahead and look at what you have and you'll say, oh, well, the symbols that are the options that I have available to me are only existing in my alternative hypothesis. Okay, so this is a greater than, so I need to arrow over to the greater than and select that. Then you're going to arrow down to calculate and you're going to hit enter. Now, what it's going to give you here is a lot of information, and 2 pieces of information that we're going to be constantly referring to are this first one, or I'm sorry, well, technically the second line here is our standardized test statistic, right? So that's what we just got here. So 2.65 if we round. The next thing that it gave us, now, and that's all this problem asked for, but the next thing that it gave us is our p-value. Okay, so remember how I was saying, we're going to be comparing our p-value to our level of significance. We can just get the p-value here without having to calculate it by hand. But we will do one where we calculate it by hand, just so you guys know where that comes from. So to reiterate how we do this problem, we either go to, oh, that's right, I was going to write it down. You're going to go to the stat button. Okay, then you're going to go to, so we go stat, we arrow over to tests, and we select the first one, which is z-test. Excuse me. So when we do that, that's going to give us both our standardized test statistic, and it's going to give us our p-value. It's going to give us both of those things. We only needed the standardized test statistic for this problem, but it gives us both those things. Okay. All right. So yeah, I know that these are super small, but the problems are super long here. All right, so the p-value for a hypothesis test is shown. So they're just giving us the p-value. Use that p-value to decide whether to reject the null hypothesis when the level of significance is, and they give us 3 different scenarios. So we're going to answer this question 3 different times. Okay, so we're going back to this rule. Is our p-value less than or equal to alpha, or is it greater than alpha? Okay, so let's look at this first one. So at an alpha of 0.01 and a p-value of 0.0373, what we have is that p is greater than alpha for this first situation. Okay. So if p is greater than alpha, I feel like this is reflecting weird. Maybe if I turn the light off. It still reflects weird. Anyway, so if our p-value is greater than alpha, then we fail to reject the null hypothesis. So that's what the answer is to this first one. Okay, so now for the second one, we have a level of significance, or an alpha, of 0.05. Again, our p-value is still 0.0373. So if we're comparing 0.0373 to 0.05, now our p-value is less than or equal to alpha. Right? This is like 3.73%. That's 5%. 3% is less than 5%. So if it's less than or, you can't see that. If it's less than or equal to alpha, we reject the null hypothesis. So we would reject the null hypothesis. And in the last situation, we have an alpha of 0.10 or 0.1. And again, our p-value hasn't changed. That's still 0.0373. So about 3%, well, 4% if we're rounding, is less than or equal to less than 0.10 or 10%. So again, we are going to reject the null hypothesis because the p-value is less than the alpha. I think in the last one I was looking at the wrong thing here. Anyway, you guys can read this for yourself. You can see when it's greater than, you fail to reject. When it's less than or equal to, you reject, right? So see how we keep referring to this? I would definitely write this down on your study sheet. Excuse me. Okay, number 8, use the calculator displays to the right to make a decision to reject or fail to reject the null hypothesis at a significance level of 0.10 or 0.1. So again, we're saying I need to compare my p-value, which is right here, with my alpha, which they're telling me is 0.1, where I can add a 0 to it. The reason that they often add the 0 to it is because they're kind of wanting to remind you that that's 10%. All right, so we have a p-value of 0.296478888. So our p-value, or really I should just be consistent here and write that p, in this case, is greater than alpha. Okay, so what happens if our p-value is greater than alpha? We fail to reject the null. So we will fail to reject the null. Right? P is greater than alpha, fail to reject the null. Okay, so now we have a whole problem from top to bottom. Well, almost. We're not determining the claim ourselves. They're giving it to us. But what we're going to do is we're going to do this by hand, and then we're going to do it in the calculator, and then that's going to be the last time we do it by hand, unless you guys really want to see it, more of them by hand, because you'll mostly just be doing them in the calculator. So give me just 1 second. Already getting a bit of a dry throat, and we're only 8 questions in, so I'm going to try and stay hydrated here. All right. So test the claim about the population mean at the level of significance alpha. Assume the population is normally distributed. So they're making sure to tell us that because in a lot of, well, not a lot, but some of these problems, our n is not going to be as high as it needs to be. And that's okay as long as it's normally distributed. Okay, so the first thing we're going to do is we're going to say, well, what was our claim? All right, our claim was that the mean is greater than or equal to 1474. I know that this is probably super small. You guys might not be able to read that, but hopefully me writing it bigger makes it a little easier. Okay, so we write our claim. Now we have to determine, did we just write down a null hypothesis or an alternative hypothesis? Our null hypothesis has some type of equality in it, and that's what we have written. So what we have happens to be the null hypothesis. So we're going to write that here. So this is kind of like separate. We're going to remind ourselves that that's our claim, and then we're going to write the complement of that. So the complement of greater than or equal to is less than, and we keep our number the same. All right, so then we're going to write the other stuff that they're giving us. I always like to write my level of significance up at the top. So let's see, what did they say that was? Oh, here, 0.02. Okay, and then they give us a bunch of other stuff. They give us a population standard deviation. Okay, so that's good. That tells us what kind of a test we're going to do. They gave us a sample mean of 1468 and a sample size of 30. Okay, so what we're going to do is we're going to start by drawing a picture of what we have going on, always based on the alternative hypothesis, right? Okay, so this is, let me, okay, all right, you're back in, Christina. Okay, so we're going to draw the picture based on the alternative hypothesis. So this is a less than. A less than means we have a left-tailed test. Okay, so what we're going to do is we are going to calculate the standardized test statistic, which is the z-score that separates the shaded area from the not shaded area. Then we're going to use that z-score to find the area of the shaded region, which is our p-value. And then we're going to compare that p-value to our level of significance, and that will tell us whether we have rejected or failed to reject the null hypothesis, and then we'll talk about how we write our final sentence from that. Then we're going to do all that in the calculator. Okay. All right. So first of all, calculating our standardized test statistic. Okay. So let's do that over here. So we're going to use our formula, which is this. Okay. So we're going to plug in 1468 minus 1474 all over 29 over square root of 30. And again, when you plug it into the calculator, please just be careful, use parentheses, or you could do it one at a time, like one calculation at a time, but I prefer to do all at once. Okay, so I'm going to go to what did they say, 2? Yeah, they want us to round our standardized test statistic to 2 decimal places. So let's go ahead and do that. That's going to be negative 1.13. Okay, so we just got this z-score right here. Negative 1.13. Also, when you when you go to plug that into your calculator, if you get a positive value, double check that you plugged everything in right, because it wouldn't make sense to get a positive value, right? Positive z-scores are to the right of the mean, and we know that this z-score is to the left of the mean, so we know we should be getting a negative value here. So if you get a positive one, go back, figure out what you did wrong. As with most things in this class, you want to be kind of checking yourself throughout the problem, making sure that your answer is making sense in the context of what's going on. Okay, so we've got our z-score. Now, what was the point of finding that standardized test statistic? It was that now that we have this, we can calculate the area to the left of it, right? So in this class, we've covered a few different ways to do that. Right, we can look it up in the table in the back of the book, where we look at the z-scores and find the z-scores are on the outside of the table and the area is on the inside. But I'm just gonna go ahead and do the calculator here. So when I have a z-score and I need to find an area, I'm going to use normal CDF. So quick reminder, that's going to be, you're going to do second, and then you're going to do the vars button, and then you're going to do normal CDF. So I'm sure we can see this. So we're going to do second. No, you can't see that. Second button, and then the vars button, which is right here, second vars. And then we're going to go normal CDF, which is number 2. Okay. And we have to give it the lower boundary of the shaded region and the upper boundary of the shaded region. Leave your mean and your standard deviation is 0 and 1. You're not plugging in any of the stuff that you have here, right? We're not doing that. We're keeping this as 0 and 1 so that we can tell it that we're dealing with a z-score, okay? All right, so my lower boundary is, well, technically it's negative infinity, right? It's all the way over here at negative infinity. So we're just going to leave this as negative 1e99. If something else is written there, that's where you would write like negative 1 times 10 to the 99th. All right, that's what you would plug in manually. All right, but our upper boundary, and I must have done this problem earlier, so I already have plugged in there this z-score of negative 1.13. Right, that's our upper boundary, that's our upper z-score. Leave your 0 and your 1, and then we say paste, and then we hit enter again, and we get this value. This is our p-value, which is the area to the left of the standardized test statistic. Okay, rounded to 3 decimal places, we're going to get this 0.129. Okay, so we have our p-value. Okay, p-value, area to the left of the standardized test statistic equals 0.129. Okay, so again, we want to be comparing that to our level of significance, our alpha. Okay, so this is greater than that, right? P is greater than alpha. So we're going to fail to reject, right? So we're going to fail to reject. Okay. Now, here is where the other chart comes in. So this is another chart that you want to have close at hand or have memorized. Excuse me. All right. So either your claim was the alternative hypothesis or your claim, I'm sorry, null hypothesis or alternative hypothesis. You either rejected the null hypothesis or you failed to reject it. Okay, if your claim was the null hypothesis, you are rejecting. You're saying something about rejecting. If your claim was the alternative hypothesis, you're saying something about supporting. Right? Do you see the pattern here in the way that these sentences are set up? If you are rejecting the null hypothesis, then you're going to say that there is enough evidence to do something. If you're failing to reject the null hypothesis, you're saying that there's not enough evidence to do something. And what is you're doing? Well, that depends on if your claim was the null or the alternative, right? Okay, so was our claim the null or the alternative? Our claim was the null hypothesis. Okay, so our claim was the null hypothesis. So we're looking at this column. And then we say, okay, we failed to reject. All right, so our claim was the null hypothesis and we failed to reject. So that's going to be this right here. So we're going to say at the 2% level of significance, there's not enough evidence to reject the claim. Okay, so, and then we would just fill that in. There is not enough evidence to reject the claim. Okay, so I know it might seem confusing at first, but if you just keep referring back to this chart, then you won't get it wrong. Right, you see how this works? The claim is the null hypothesis, and we failed to reject the null. Where do they intersect? They intersect in this one right here. Okay. And if you're having trouble seeing the patterns of like, oh, claim that talks about supporting, or failing to reject that talks about is not. Also, it doesn't help that my orange and my red kind of look similar. Anyway, so that's what you're going to be referring back to. Okay, so we did all of that by hand. Now, let's do that in the calculator. Now, the first part of what we do is going to be almost exactly the same. So if we were to do this problem again from the beginning, but in the calculator, we would still start out by writing out the claim. We would write out, okay, that was our null hypothesis. Then we'd write out our complement of that, which is our alternative hypothesis. We would draw a picture to remind us that we are left-tailed test. And we would write down all the things that they gave us. But then what we'd do is we'd go to stat, test, and what is it, number 1? I forget. Stat, test, and yeah, number 1, Z test. Okay, and we're going to enter in everything that we have here. So what number did we have associated with our null hypothesis? 1474. What was our population standard deviation? That was 29. What was our sample mean? That's 1468. What was our sample size? That was 30. What was the alternative hypothesis? This was a less than. So I'm going to make sure I have less than highlighted. And then I'm going to say calculate. And if they ask me specifically to provide them the standardized test statistic, okay, well, I can give that to them. But what I'm really after here is my p-value, right? This 0.129 if we round to 3 decimals, which they told us to do. Once I have this p-value, now I'm going to compare it to my alpha. And I'm going to say, oh, okay, so this p-value is greater than alpha. Okay, what does my rule say to do? What's the decision rule? P-value is greater than alpha, I'm going to fail to reject. Okay, how do I word that when I fail to reject? When I fail to reject and when my claim is the null, I say that there's not enough evidence to reject the claim. Right? There's not enough evidence to reject the claim. So either way you do it, oh, you couldn't see when I was writing that over there. Oh, sorry, I hate that these are, there's so many words on each of these problems that I have to make them so tiny and then you can't see them. Yeah, so if you want to do it fully in the calculator, you still have to do like this, right? You still have to start out with this. I mean, you don't technically have to write that down, but you want to be keeping that in mind. And then you do this. Okay, so we did it by hand, and for the rest of them, we're going to do it in the calculator. Okay. All right. Okay, number 10, use technology. So they're even reminding you like, hey, don't forget, you can use technology here to help you test the claim about the population mean mu at the given level of significance alpha using the given sample statistics. And again, they're reminding us that well, they're telling us that we can assume that the population is normally distributed. Now, in this case, our N is 200, so we're fine. We've got enough of a sample size that that's not an issue, but it's always good to be told that it is normally distributed. All right, so just like we always do, the first thing we're going to do is we're going to write out, okay, what was our claim? Sometimes they give us the claim in words. Here, they gave it to us in symbols, so that's one less thing for us to do. We're not translating the words into symbols. It's already there. Okay, that's my claim. Great. Now we're going to say, okay, did they just give us a null or did they give us an alternative? The null always has some type of equality, and this does. So they have yet again given us a null. It's not always the case, but it is here again. Then we're going to write the complement of that, which is our alternative hypothesis. The complement of less than or equal to is greater than, and you keep your number the same. Then we're going to draw ourselves a little picture based off of our alternative hypothesis. Greater than is a right-tailed test. Okay. All right. So just because everything that they give us is so small, I'm going to rewrite it bigger. So our level of significance, our alpha, is 0.06. And then they gave us that our population standard deviation is 199.31. They gave us that our sample mean is 1282, 0.15, sorry, and our sample size is 200. Okay, so I like to go through and just kind of solve these from beginning to end and then go fill in the specific things that they're asking for. But a little caveat to that, don't do more work than you have to. Like if one of the first problems we did, all they asked for was the the standardized test statistic. That is a mouthful. So you wouldn't want to go through and solve the entire problem and find your p-value and compare it and write your sentence about what is the conclusion. You don't want to do all that if all they're asking for is your standardized test statistic. But if they are asking for the whole kit and caboodle, which they are here, then sometimes it's easier to just go ahead and do the whole thing first and then fill in. Now, I'm not entirely sure if when you guys do these problems, if they kind of show up one piece at a time. I mean, it does tell you, yeah, I'm not sure. Yeah, because I've seen some different interfaces before where like once you do this, only then will this pop up for you to fill in. And then I've seen others where it gives you all of this and you can like kind of fill things in whatever order you want. But if you do see that you're being asked to do all this stuff, then you can go ahead and do it and then go fill it in. But if you don't know how much you have to do, don't do any more work than just the question that's sitting right in front of you. Okay, so yeah, we're going to do this in the calculator. So we were given a population standard deviation. So we're going to go stat and we're going to go tests and we're going to go number one to what was it again? Number one, pretty sure it was number one, z-test, right? Stat, test, z-test. And we're going to fill in what they've given us. Okay, so the number associated with our null hypothesis is 1250. And I mean, really, that's the same number as your null and your alternative, but they're just kind of reminding you, like, hey, don't forget to get it from, like, excuse me, from, these and not from your sample, right? Okay, population standard deviation, plug that in. Sample mean, make sure I'm plugging in the right numbers here, sample size. And then we use our alternative hypothesis. This is greater than, so I'm going to arrow over to greater than, and then we're going to hit calculate. Okay, so it does give us our standardized test statistic, which is 2.28. Okay, and it does give us our p-value, which if we round to 3 decimal places is going to give us 0.011. And so the calculator did all of that for us, and now we have to draw the correct conclusion from that, right? So if I have a p-value of 0.011 and I have an alpha of 0.06, then that means that my p-value is less than or equal to my alpha, right? If my p-value is less than or equal to my alpha, I'm going to reject my null hypothesis. Okay, so I'm going to say, all right, I reject the null. Reject the null. Right, so your first thing, well, not first thing, but when we're at the end here, when we're talking about, okay, what's the conclusion of the test? We say, first step, do we reject it or do we fail to reject it? Once you've determined that, then you can go to your other chart and you can say, okay, I've rejected it. And Mike, oh, you know what I didn't do? I normally always do that. I normally always write claim next to whichever one of these was the claim. In this case, the claim was the null. So we rejected the null and the claim was the null. So the way that we're going to word this is that there is enough evidence to reject the claim. So we say there is enough evidence to reject the claim at the 6% level of significance. Okay. So it still takes a little bit of time to do these, but much faster if you're just plugging them into the calculator doing this, rather than plugging in numbers into your standardized test statistic formula to find that z-score, and then using that z-score to find the corresponding area. And then you can go ahead and compare that area, that p-value, to your alpha, right? So a lot faster to do it in a calculator. Okay. Number 11. A nutritionist claims that the mean tuna consumption by a person is 3.2 pounds per year. A sample of 90 people shows that the mean tuna consumption by a person is 2.9 pounds per year. Assume the population standard deviation is 1.19 pounds at an alpha of 0.07 or a level of significance of 0.07. Can you reject the claim? All right, let me get a drink quick. All right. So this one, they didn't just give it to us in symbols. So we have to write out, we have to translate, right, from the words to the symbols. Okay, so we're going to say, all right, what was our claim? Well, they said that a nutritionist claims that the mean tuna consumption by a person is 3.2 pounds per year. So the claim they're making is that the mean tuna consumption is or equals 3.2. That's the claim. Okay, so now we need to say, all right, did we just write a null hypothesis or did we just write an alternative hypothesis? So the null hypothesis always has some type of equality in it, and this does. So they just gave us a null hypothesis. Okay, so now we need to write its complement, the alternative hypothesis. So the complement to equal is not equal. Right? The next step, now that we have both of our null and our alternative, is that we're going to draw a picture based on the alternative hypothesis. So if we have a not equal to, if you remember from one of the first ones that we did, not equal to is two-tailed. Okay? So we haven't done one of these yet, but quick reminder, that's supposed to be even, the area on that side and the area on that side. Keep in mind that this is 1/2 of your p-value, right? And this is 1/2 of your p-value. And that your standardized test statistic, you're going to have both a negative and a positive, right? Okay, so let's go ahead and start labeling everything else, All right, so their alpha, I always like to write that first. Alpha is 0.07. Okay, what else did they give us? A sample of 90 people, that's n, is 90, shows that, so that sample showed a mean, so that's a sample mean of 2.9. And then they did give us a population standard deviation of 1.19. Okay, so since they did give us a population standard deviation, we are going to be using that same test that we've been doing, right? We're going to go stat, tests, number 1 z-test. And we're going to plug in what we have. So the number associated with our null hypothesis is 3.2. Our population standard deviation is 1.19. The x-bar, our sample mean, is 2.9. Our sample size is 90. And we have a not equal to, right? That's our null hypothesis is a not equal to. And then we're going to say calculate. Okay, so we have a z-score. Now, it's giving us the negative, but it's both the negative and the positive. You can see here that it's fine to just give them the negative. You don't have to give them both of them, right? So we have the z-score of negative 2.39. They want us to go to 2 decimal places. And then we have the p-value. So they're not asking for the area, they're asking for just the p-value itself, right? So we're just giving them the number that we see here, the 0.016, or if we rounded to 3 decimal places, sorry, that's 0.017, right? 0.017. Now, if you're doing this like by hand, and because I spoke briefly about how there's multiple ways to figure out the final answer, like, are we rejecting the null or not rejecting the null? So comparing your p-value to your alpha, to your level of significance, is the easiest way to do it. But other ways that you can do it is by like looking at each of these individually and seeing where something falls. Like, oh, does something fall in what's called the rejection region? So from what I can tell, you guys are not being asked to do problems where you're looking at what's called the rejection region, okay? So we're not going to get into that because you guys don't need to do that. You guys are, from what I can tell, you're going to be able to just say, what's my p-value? Let me compare that to my alpha, and you'll be just fine, okay? Yeah, okay. So we've got our p-value. P-value 0.017. What was our alpha? It was 0.07. Okay, so my p-value is less than my alpha. So what happens when your p-value is, less than or equal to, right? Less than or equal to my alpha, I'm going to reject the null. Okay, great. I rejected the null. So right off the bat, I can rule both of those out because they say fail to reject, but we're rejecting. Then we say, okay, how am I supposed to word this? I know I'm rejecting the null. Right, reject the null. And then we say, was the null my claim or was the alternative my claim? The null was my claim. So my claim is null, and I'm rejecting the null. So I'm going to say there is enough evidence to reject the claim, is how I need to word that. So there is sufficient evidence to reject the claim. And then we're going to go ahead and state, well, what was that claim? There is sufficient evidence to reject the claim that the mean tuna consumption is equal to 3.2 pounds, right? So it's always a good idea to kind of circle back around and say, sort of like, what does this mean? Like, I look at, this nutritionist is making a claim and we're saying, yeah, no, there's sufficient evidence to reject that claim that they made, right? That's the whole point of this, is we're testing a claim, we're testing a hypothesis. And we found that we're able to reject the claim that this person made. Okay. All right, start reading before I even get it on the page there. Find the standardized test statistic for a sample with, statistic T. So it's telling us specifically this is going to be T for a sample with N equals 15, sample mean 3.9, sample standard deviation 0.8, and level of significance of 0.05. If your null hypothesis is that the mean is less than or equal to 3.6, and round your answer to 2 decimal places. Okay, so again, we are going to, excuse me, we're going to be doing this in the calculator, right? So we have, because that's going to be faster, right? So let's write everything out so that we can kind of see it better, right? So we have that our null hypothesis, they told us, was that the mean is less than or equal to 3.6. So that means that our alternative hypothesis is the complement of that, okay? And then if we draw a picture, it's greater than, so this is a right-tailed test, okay? They gave us a level of significance, an alpha of 0.05, and then they gave us an N of 15. Quick note here, if you want to do this by hand, don't forget that your degrees of freedom is N minus 1. So in this case, that would be 15 minus 1. So that would be 14. Oh, sorry about that. I'm kind of squished here at this desk and I just knocked the phone over. Okay, what else did they give us? They gave us a sample mean of 3.9, and they gave us a sample standard deviation of 0.8, which, by the way, if they hadn't come out and told us specifically that this is a T, we would have known, because we have a sample standard deviation, not a population standard deviation. And if we don't have a population standard deviation, then we can't use the Z, we have to use the T. Okay, yeah, so that's all they gave us. So very similar to, try to make sure this fits on the screen here. To what we have been doing, we're going to go to stat, and we're going to go to tests. Right, so we go stat, tests, but we're, instead of doing number 1, we're going to go number 2. This is a t-test. T-test. All right, so we're going to plug in what we've got. Okay, so the number associated with our null hypothesis is 3.6. Our sample mean was 3.9. Our sample standard deviation was 0.8. Our sample size is 15. And the null hypothesis was a greater than symbol here. And then we go down to calculate. Okay, so they asked for, all they wanted here was the standardized test statistic, the t-value. So we have this t-value right here of 1.45. And that's, sorry, you can't see that. That's how we get the 1.45. Okay. Okay, so that was a warm up, because now they want us to do a full problem with t-tests. Okay, use t-test to test, so they're reminding you, hey, this one's a t-test, not a z-test, to test the claim about population mean, mu, at the given level of significance alpha, using the given sample statistics. Assume the population is normally distributed. All right, so again, we have a claim. They told us that the claim is that the mean is greater than or equal to 7,900. So before I do anything else, I'm going to say, okay, did they just give me a null or did they give me an alternative? They seem to be giving us a lot of nulls lately. That's not always the case. It's you never know which one it's going to be. But this is a null because it has some type of equality. Whereas alternative hypotheses are strict inequalities. So I need to label that's my claim. So the complement to this is this. Okay, now that I've labeled both my null and my alternative, I'm going to draw a picture of what we have based on our alternative. This is a less than symbol, so this is a left-tailed test. And we're going to write, okay, what was our level of significance? It was 0.05. Let's go through and label everything else they gave us. They gave us a sample mean of 7,600 and a sample standard deviation of 430 and a sample size of 24, which it's good that they told us that it's normally distributed because that's not a big enough sample size otherwise, right? If it wasn't normally distributed and we had a sample size less than 30, that would be a problem. But it's okay that this is a small sample size because it is normally distributed, right? So that's like telling us that the T is acting more like the Z. Okay, so let's go ahead and plug this in so that we can find the standardized test statistic and the p-value, and then we are going to compare our p-value to our alpha to determine if we reject or fail to reject the null, and then we're going to look at the chart to say how we word our final conclusion based on whether we rejected the null or failed to reject it, and whether our claim was the null or the alternative. Okay, so we're going to go to stat. Oh, I'm already here. But stat, test, arrow down to t-test. Okay, the number associated with my null hypothesis is 7,900. My sample mean is 7,600. My sample standard deviation is 430. My sample size is 24. And the symbol associated with my alternative hypothesis is a less than symbol. And I arrow down to calculate and enter. Okay, so I am getting, when I round to 2 decimals, a t-score of negative 3.42. Makes sense that it's negative because it's to the left of the mean, so that's good, that makes sense. And then I'm getting a p-value, if I go to 3 decimal places, of 0.001. Okay, so I have a p-value of 0.001. and I have an alpha of 0.05. So my p-value is less than my alpha. So do you have it memorized by now? So if my p-value is less than my alpha, which less than or equal to, apparently I don't have it memorized by now, p-value less than or equal to alpha, we're going to reject the null. Okay, reject the null. Okay, that's nice. Now what do I do with that? Now that I know that I'm rejecting the null, I'm going to look at if my claim was the null or the alternative. My claim was the null. So my claim is the null and I'm rejecting the null. Where do these things overlap? They overlap right here. There is enough evidence to reject the claim. So I reject the null, and at this level of significance, there is enough evidence to reject the claim. Right? Rejected the null, claim is the null. There is enough evidence to reject the claim. Okay. Number 14. Test the claim about the population mean, mu, at the level of significance alpha. Assume the population is normally distributed. So they're not telling us which one we're going to use here, so we need to figure that out. They're giving us a claim of the mean is less than 5,015. So the first thing I'm going to do is I'm going to say, did they just give me a null or did they give me an alternative? So the null contains some type of inequality, and this is, I think, the first one that we have where our claim does not have that. The alternative is the one that has a strict inequality. So they finally have given us an alternative. So the claim is the alternative. Okay, great. So now we need to say, well, what is the complement of that? What is my null hypothesis? The complement of less than is greater than or equal to with the same number. All right, and what is my alpha? What's my level of significance here? 0.1 or 0.10. And let's go ahead and write out everything else they gave us. They gave us that the sample mean is 5117, that the sample standard deviation, okay, so we have a sample standard deviation as opposed to a population standard deviation, 5725, and our n, our sample size, is 53. Okay, so they didn't tell us which one to use, but we do not have a population standard deviation, so we can't use z. This tells us that we need to use a t-test. So we're going to go stat, tests, and then 2, t-test. Okay. Stat, test, 2, t-test, and we're going to plug in what we've got. The number associated with our null hypothesis is 5015. Sample mean is 5117. Sample standard deviation is 5725. Goodness, that's a big standard deviation, isn't it? Wow. Okay. Sample size is 53. Excuse me. And our the symbol related to our alternative hypothesis is the less than, which happened to already be highlighted, and then we calculate. Okay, so they want our standardized test statistic. It's quite a mouthful. In this case, that is our t value, right? This 0.12970677613, which if we go to 2 decimal places is going to be 0.13. And then we have our p value, which is this 0.551, because they asked us to go to 3 decimal places there. Okay, so I've got a p-value, which again, if you're doing this by hand, in order to calculate the p-value, you first have to have your standardized test statistic. Well, you know what I didn't do? I didn't draw a picture. Let's draw a picture. This is less than, so that's a left-tailed test. The one time I don't draw a picture, I start talking about referring to it. So remember, if you're doing this by hand, the first thing you do is find your standardized test statistic by using the formula to find this value, and then the p-value is the area to the left of that, right? I don't think I gave you that formula because we did it in the calculator. I should probably give you that formula. Honestly, I don't remember it off the top of my head. That's fine. Let's just look it up real quick. So this is going to be in 7.3 because 7.3 is when you don't know the mean. Here we go. So it's very similar. It is your sample mean minus your population mean all over your sample standard deviation over the square root of n, right? So almost exactly the same, except instead of the population standard deviation, you use your sample standard deviation. And then also you have to remember that when you go to look that up in the back of the book, that you have to take in mind your degrees of freedom is n-1, right? Okay, but we're not going to do it by hand, are we? We're going to do it in the calculator because it's much easier to do it that way. All right, the point is that we have our p-value, which is the area, sorry, you can't see that, the area to the left of our standardized test statistic. Our p-value is 0.551. Our level of significance, our alpha, was 0.10. So our p-value is greater than our alpha. And what happens when p is greater than alpha? We fail to reject the null. So fail to, got the hiccups apparently, reject the null. All right, we're failing to reject the null. What other piece of information do we need before we go and look at our other chart? We need to know if the null was our claim or if the alternative was our claim. The alternative was our claim. So we've failed to reject the null and our claim was the alternative. So we failed to reject the null and our claim is the alternative. So we say there's not enough evidence to support the claim. Okay, not enough evidence to support the claim. So there is not enough evidence to support the claim. And then we go through and we just fill in everything that we just found, but in the way that they want it. Okay, so they want that our null hypothesis is that the mean is greater than or equal to. Our alternative hypothesis is that the mean is less than that. Okay, we found those two numbers. We fail to, I did not leave enough room there. Fail to reject the null hypothesis. And there's not enough evidence at this particular level of significance, which is 10%, to support the claim. Not enough evidence to support the claim. All right. Okay, so we have another one where they're telling us specifically this is going to be a t-test. Use a t-test to test the claim about the population mean at the given level of significance using the given sample stats. Assume it's normally distributed. That's good because we got a tiny little sample size here of only 13. So good thing it's normally distributed, otherwise we wouldn't be able to do this. All right, so our claim is that the mean is not equal to 24. So we have to determine if that is our null or if that is our alternative. So our null always has some type of equality, and this does not. This is a strict inequality. So again, they happen to give us an alternative hypothesis. That was our claim. Now that we have one, we have to write the other. So it's the complement of that. So the complement of not equal to is equal to. Then we're going to draw a picture based on our alternative. This is a two-tailed test. Okay. And I'm going to write my alpha, which is 0.01, so 1%. Okay. And I'm going to go ahead and label everything else that they've given us. So I've got a sample mean, 26.8. I've got a sample standard deviation, 4.4, and I've got that tiny little sample size of 13. So even though they told us it was going to be a t-test, if they hadn't told us that, the fact that we have a sample standard deviation and not a population standard deviation tells us that this is going to be a t-test. Stat tests to t-test. Ugh. Okay. Stat test t-test and plug and chug. So the number associated with our null hypothesis is 24. Our sample mean is 26.8. Our sample standard deviation is 4.4. Sample size is 13. And the symbol associated with our alternative hypothesis is not equal to. And then we calculate. We have a standardized test statistic of 2.29. We have a p-value of 0.041. If we go to 3 decimal places, that rounds to 0.041. Okay, so I have a p-value of 0.041. I have an alpha of 0.01. So my p-value is greater than my alpha. And what happens when p is greater than alpha? We fail to reject the null. Fail to reject the null. And so I haven't been doing this, but it would probably be helpful. I'm going to do it from now on. If after you write whether or not you fail to reject the null, like if you reject it or fail to reject it, maybe under that, go ahead and write, what is my claim? My claim is the alternative. And that way you've got kind of all of that information right there in the same spot for when you go to look at your chart, right? So fail to reject null, claim is alternative. Fail to reject null, claim is alternative. So there's not enough evidence to support the claim, is how we're going to word this. So we say, fail to reject null, there's not enough evidence to support the claim. Okay. Okay, a research center, is this light on? That might be a little easier. Okay. A research center claims that 28% of adults in a certain country would travel into space on a commercial flight if they could afford it. In a random sample of 1,200 adults in that country, 32% say that they would travel into space on a commercial flight if they could afford it. At an alpha or level of significance of 0.01, is there enough evidence to reject the research center's claim? Complete parts A through C below. All right, so again, we're just kind of doing this problem from top to bottom, but we have to remember that this is a proportion, right? Because we're talking about percentages here. Okay, so when we're dealing with percentages, we need to remember, make sure I'm writing where you guys can actually see, that your p hat is your x over your n, right? So when we go to use the calculator for this, we need to have an x and we need to have an n. They're not giving us an x and an n. You know what? I'm getting ahead of myself. Let's start the way that we always start. What's the claim? The center claims that 28% of adults, so the proportion is 0.28. That's the claim. The claim is that the proportion of adults that would do this is 28% or 0.28. Okay, is that a null or is that an alternative? The null is the one that has an inequality, so that one is the null. So the claim is the null. So now I'm going to write the alternative, which is the complement of that, which is not equal to. We'll draw a picture based on the alternative. This is a two-tailed test. And because we're dealing with a proportion, our standardized test statistic is going to be a z-score, not a t-score. Okay, so now let's talk about the p hat, the sample proportion, is x over n. So there's a couple of different ways you can approach this. So they have said that 32%, so in this sample, so n, this sample of 1,200, that 32% said that they would travel into space. So that means that p hat is 0.32, right? So if p hat equals x over n, then I can rewrite this equation and say that that means that 0.32 is equal to x over 1,200. Okay? So, oh, I don't have my pen. Of course I don't have my pen. I wasn't expecting to do colored pens today. Okay, we're just going to use a black pen because that's what's sitting right here. So in order to solve that equation for x, right now it's being divided by 1,200. So to get rid of dividing by something, I'm going to multiply by that thing. So I'm going to multiply both sides by 1,200. So if I multiply and divide by the same thing, they cancel. And I get that x is equal to, and in the calculator, we're going to say 1,200 times 0.32 is 384. Okay, because I needed to know my x and I needed to know my n. My x is 384 and my n is 1,200. Okay, now that's how you would do it if you're not quite sure what's going on and you're just gonna plug the numbers into the equation and then solve. But if you have a more holistic's not the right word. If you kind of have a better understanding of what's happening, you can say, well, if it's 32%, then I just need to find 32% of 1,200 people. right? And how do we do that? 32% of 1200 is 0.32 times 1200, right? And math of means multiplication. So 1/2 of something is 1/2 times that thing. So 0.32 times 1200, and that's getting you the 384, right? So if you want to just jump straight to, oh, well, 32% of the sample size is this many people, and just plug it in real quick into your calculator like that, go for it. If you find that you're having trouble knowing what you're supposed to be doing here, then set up your equation, solve your equation with your algebraic rules. Okay, so we have our x, we have our n. What else did they give us? They gave us our alpha. Oh, I didn't write my alpha where I usually like to write it. I usually like to write it higher. I guess I'll just write it over here. It's 0.01. Okay, so now this is a proportion, right? This is not the ones that we've been doing before, where we have a sample mean or a sample standard deviation versus a population standard deviation. So what test are we doing? So it's in the same menu, right? It's still stat, and then it's tests, right? We're still doing a hypothesis test, but you're going to go down to one. What number is this? I don't remember what number it is. It's one prop C, one test, one prop C test. So that's number 5. Here, let me erase that. I'm going to go all the way down to number 5. One prop Z test, right? So this is the menu that we use when we're doing the proportion. All right, so now we're going to plug in everything that we have. All right, so what is the number that is associated with our claim? So, or our null hypothesis, that's 0.28. Okay, our x, right? That's why we did all that work, because we need to know, we need to tell it specifically what our x is. 384. Our n is 1200. And then we have to tell it what symbol was used in our alternative hypothesis, which is a not equal to. And then we arrow down to calculate and enter. Okay, so we have our standardized test statistic of 3.09. If we go to 2 decimals, get this out of the way here. And then we have our p-value of 0.002 if we go to 3 decimals. Also, you'll notice that it calculated p hat for us, right? It gave us that p hat was 0.32. So in this particular problem, we actually already had that, and we had to work backwards to get the x and the n. But sometimes you're not given the p hat, you're just given the x and the n, and it's always going to just kind of spit that out for you. So that's always nice to have. Okay, so we have our p-value is 0.002. Our alpha was 0.01. So P, I'll write it down here, I'm running out of room, is, what is that? That's less than alpha. So what happens when P is less than or equal to alpha? We reject the null. Okay, so I'm going to reject the null. And then what was my claim? My claim was the null. Okay. So I'm rejecting the null, and my claim was the null. Reject the null, claim is the null. There is enough evidence to reject the claim. So you guys can't see that. There is enough evidence to reject the claim. And I mean, I just jumped down here, but really, I guess we should probably fill things in from the top. Okay, so identify the claim and state the null and alternative. So 28% of adults in the country, this is the claim, would travel into space on a commercial flight if they could afford it. Sorry. I thought they were just talking. Yeah, identify the claim. That's what this first part is. Identify the claim. The claim is what they said. 28% of adults would do that. Okay, now they want us to say what's the claim and what's the alternative. That's what we did up here. The claim is P is equal to 0.28. The alternative is P is not equal to 0.28. Then we found our standardized test statistic in the calculator, and we found our p-value in the calculator. We rejected the null because the p was less than or equal to alpha. And then based on the fact that we rejected the null and that the claim is the null, the way that we word our final decision is that there is enough evidence to reject the research center's claim. All right. Okay, a humane society claims that less than 70% of households in a certain country own a pet. In a random sample of 600 households in that country, 402 say they own a pet. At an alpha of 0.01, is there enough evidence to support the society's claim and complete all the parts? So again, we're just going to go from the top, solve the whole thing, and then fill in the answers that they want after I have a quick drink. Okay. What is the claim? A humane society claims that less than 70% of households own a pet. So that's a percentage, that's a proportion. So that's that P is less than 0.7 or 0.70 if you want to remind yourself that that's 70%. Okay, that's my claim. Now, did I just write a null or did I just write an alternative? So the null has some type of equality. This does not. So we just wrote an alternative hypothesis. So remind ourselves that that one's the claim. The other one, in this case the null, is going to be the complement of that. So the complement of less than is greater than or equal to. Okay, we're going to draw a little picture of what type of test we're doing. This is less than, so that is a left-tailed test, right? And we are going to write what our alpha is. They said that it was level of significance of 0.01. Okay, so let's write down the rest of the stuff they gave us. They told us that we have a random sample, so n, sample size of 600 households, and from that sample, 402 of them said they owned a pet. So that's nice. They gave us our x and our n directly rather than giving us our p hat. If they had given us our p hat, we would have had to have worked backwards like we did in the other problem to figure out what the x is. But they just gave us the x, so that's nice. Okay, so I think we have everything we need in order to plug this into the calculator. So again, this is a proportion. So we're going to be going to stat. We're going to close out of that. We're going to go stat, tests, and then go down to number 5, 1 prop z test. Prop like proportion, right? And we're going to plug in what we have. So our sample, I'm sorry, our null hypothesis, we have 0.7. Our x is 402. Our n is 600. And the symbol associated with our alternative hypothesis is less than. So we're going to arrow over to that and then calculate. Okay, so we have a a standardized test statistic that is a negative z-score. Makes sense that it's negative. This is left-tailed. It should be negative. So that's good. And if we go to 2 decimals, it's 1.60. And we have a p-value of 0.054 if we go to 3 decimal places. Also, again, they gave us our p hat if we wanted to know that, our x over our n. Okay, so we have a p-value of 0.054. We have an alpha of 0.01. So our p-value is greater than our alpha. What happens when our p-value is greater than our alpha? We fail to reject the null. So fail to reject. Okay. And then my claim is the alternative. I always emphasize the little tail on the A so that I don't think that I've written in a 0. And we're going to see if I fail to reject, sorry, I need to clarify there, fail to reject the null, and the claim is the alternative. Fail to reject the null, claim is the alternative. There's not enough evidence to support the claim. So that's how we word this down here. There is not enough evidence to support the claim. All right, and then now let's go back and fill in everything the way they want it filled in. So identify the claim. So we said that the claim was that the proportion is less than 0.70, so less than 70% of households in the country own a pet. And written out in symbols, the alternative is p is less than 0.70. The null is p is greater than or equal to 0.70. We identified the standardized test statistic. The calculator shot that out for us, as well as the p-value. And then we used that to say that we failed to reject the null. And that, along with the fact that our claim was the alternative, told us how to word our final conclusion and interpretation. There is not enough evidence to support this society's claim. Okay, now moving on to chapter 9. So for chapter 9, correlation coefficients, linear regression, there's, you know what, let's just dive right in. Okay, which of the following values could not represent a correlation coefficient? So your R value, your correlation coefficient, has to be between -1 and 1 inclusive, meaning it's allowed to be -1 and it's allowed to be 1, but it has to be somewhere in between there. Can't be less than -1, can't be more than 1, right? So like if we're picturing this on a number line, we have -1, we have 1, zeros in the middle here, right? It can be anywhere in between and it can be them, but it can't be beyond, right? So we can't have 1.032 because that's beyond the positive 1. So when we talk about having a strong correlation, that strong correlation can either be a positive correlation or it can be a negative correlation. You can have a strong negative correlation and you can have a strong positive correlation. The closer you get to 1 or -1, the stronger the correlation. But the closer you get to 0, the weaker the correlation. Okay, so closer I get to 1 or -1, the stronger the correlation. It's just, is it positive or negative correlation? The closer I get to 0 from either side, the weaker the correlation. Okay. Your correlation, if you have a positive correlation, then your data values have a positive slope. If you have a negative correlation, your data values have a negative slope. And if you have a weak correlation, then you're all over the place. You're drawing a line of best fit is difficult. Okay. All right. think we did a little bit more than what that asked there, but that's okay. All right. Calculate the correlation coefficient R for the data below. Now, as with most things in statistics, you've heard me say this a million times, I bet you're sick of hearing it. It's important that you know that there is a formula to do this. But in this class, you are not being asked to use the formula and to do it by hand. You are being asked to know that there is a formula and then to use the tools that have been created and that are at your disposal to do it the fast way. So the formula for the correlation coefficient is this big long thing. Like here, let me get the book up. Your instructor does not want you to do this by hand. They want you to do it in the calculator. Okay, so the formula, I'm not even going to change the zoom on this. This is the formula for the correlation coefficient. That looks fun, right? Actually, it is kind of fun. They even have step-by-step directions on how to plug the numbers into the formula and get an answer, right? The formula is so involved that they have to have directions on how to plug numbers into a formula. It's not normally something that they do, but this one is so involved that they do it. So we're not going to do it. We're just going to have the calculator do it. Okay, now having the calculator do it is a little involved. If you are having some trouble getting your calculator to do what it's supposed to do with chapter 9, reach out to me, let me know by email. But also I am going to, I had this piece of paper and I scanned it in, and so this is, sorry, give me a second, because I just want to show you this part of it. So I have some notes here. Yeah, you guys probably can't read this very well, but in order to make sure that your calculator is displaying things the way it's supposed to, you have to go into this, like you have to turn diagnostics on. So if you haven't done that, you might have an issue. Also, if you want to be able to see your equation, you have to like go into a particular menu to select like Y1. There's a lot of like very specific things to do with this. So I'm not going to talk about turning the diagnostics on, but I will send you guys these notes as an attached PDF so that you can look at them if you need to. This isn't super detailed or super like well written. It's just kind of quickly writing out kind of some of the stuff that we're going to need to do. Okay, so let's actually do one of these. So calculate the correlation coefficient R for the data below. All right, so what we're going to do is we are going to plug this in to our L1 and our L2. Now, previously, you guys have seen L1 and L2 as like vertical lists, right? Well, you're just seeing them as horizontal lists. Your X value is your L1, your Y value is your L2, okay? So quick recap, if you guys remember was it the first chapter? Second chapter? You did stat, sorry, you can't see that, stat, and then you did edit, and you had all your lists, right? So you're going to go over to L1 and L2, and you're going to plug these in. So type each of these in for L1, type each of these in for L2. So I've already done that, so that I don't have to waste time doing that. Okay, so then what are we going to do? So what we're going to do is kind of, you know what, I'll write it out by hand here, but I do have this on the PDF here. We're going to go to stat, and we're going to go to tests, and then we're going to go all the way down to F, which is linear regression t-test, right? So I'm going to go stat, test, and then I'm going to arrow all the way down to F, linear regression t-test. Okay, then I need to tell it which list it needs to look at. So I was doing other stuff in here, so right now it's looking at other lists. I need to tell it, no, look at L1 and L2. So quick reminder, L1 is here above your 1, so you're going to hit second 1, and that puts L1. Okay, so for the Y list, I'm going to do second 2, and it puts L2. You're going to leave your frequency at 1. You're going to leave this at whatever it's at. It's probably less than 0. Just leave it there. All right, your regression equation. So this is what I was talking about with the Y1. If Y1 is not sitting there, what you're going to do is you're going to go to vars, and then you're going to go, my directions aren't very clear. Let me actually go ahead and do that to make sure that that's what it is. So we go vars. Oh, and then we go, that's what it was. We go vars, and then you go over to y vars, okay? And then number 1 function, and then y1. Okay, so you make sure your y1 is there. Okay, and then we go down to calculate. Okay, so it's going to spit a lot of stuff out to us. Okay, so let's start by just answering the question that it asked us, and then we'll talk about this other stuff it's displaying. So it asked us for the correlation coefficient R. You got to arrow down for that. Got to arrow down a couple of times, and there it is. Now they want us to go to 3 decimals, so just make sure that you're being careful when you're rounding. So 0.989 rounded to 3 decimals is 0.990. Okay, now what about all this other stuff it's giving us? Okay, so for those of you that took algebra somewhat recently, maybe you remember, you've heard of y equals mx plus b. That's kind of what's happening here, right? We have a line, but we're not going to be using those letters because the b is not the b here, okay? But what the calculator is going to give us is y equals a plus bx. And we have to, for everything that we're going to be doing, remember that we're going to switch our 2 terms here, our a and our bx. We're going to write the bx first, and then we're going to write the a term. Okay, so that's just something to be aware of, right? So it reminds you that what it's giving you is y equals a plus bx, and then like if we arrow back up, so it's here's our a and here's our b. Right? So that's going to be stuff that we're going to look at in the next few problems. Okay. Okay, the data, you can't see that. The data below are the number of absences and the final grades of 9 randomly selected students from a stats class. Calculate the correlation coefficient, right? We're trying to see, is there a correlation between the number of absences and the final grades, right? Okay, so again, we're going to put this in L1 and L2. I'm going to put it in L3 and L4 because that's what I did so that I could have all of these already in here. So you're going to go to Stat, Edit, and you're going to put them in their list. Like I said, excuse me, I'm doing 3 and 4 just because that makes it easier so I don't have to type all these lists in live. Okay, so I have L3, L4. So now I'm going to go to Stat, Tests, and I've probably shown you guys this before, but a quick refresher that instead of arrowing down, if you arrow up, if something is near the bottom of the list, it's fewer clicks, right? Also, if you already know exactly what it is, so I go to Stat, Test, if I know that it's the letter F, then I can also just type in F and it'll go directly there. So remember that, so on my calculator, the alpha is yellow. And so the F, you probably can't see this in this light, but the letter F is above my cosine button in yellow. So this acts kind of like a shift. So I can say alpha F, and it just selects that letter. Okay. All right, so I need to update it, and I need to say, no, please look at L3 and L4, but everything else stays the same, and we calculate. Okay, and then we're going to arrow down, and we have an R of negative 0.9907, 827,837, which when rounded is negative 0.991. That is a super strong correlation, right? Because it's really close to -1. Okay, so if you're between, and we talked about this before, but just as a quick reminder, let's go back to, is it? Yeah, here we are. So if you're between 0 and -1, the closer you are to -1, the stronger your correlation. If you're between 0 and -1 and you're closer to 0, you have a weaker correlation. And then the same is true for if you're between 0 and 1, the closer you are to 1, the stronger your correlation. If you're between 0 and 1, the closer you are to 0, the weaker your correlation. Okay? So applying that to this problem, we have a correlation coefficient of -0.991. That is a very strong correlation. So there is a strong correlation between the number of absences and the final grades, right? Makes sense. Don't go to class, probably not going to get a good grade. Okay. All right. Which actually leads nicely into which value of R indicates a stronger correlation. And then they give us two values. So they give us a positive number and they give us a negative number. But we're not worried about, do I have a positive or a negative correlation? We're worried about, do I have a strong or a not as strong, or maybe a weak correlation? So you can either just kind of picture what's happening on the number line. Right, so I have 0, I have 1, I have -1. Right, so this is 0.832, so that's somewhere over here, right? 0.832, and this is negative 0.947. So you can either say, well, which of these numbers is closer to their sort of respective thing that they're trying to get towards? This is closer to -1 than this is to 1. However, a lot of people kind of struggle with that. So a kind of fast and easy way to do it is say, well, just compare their absolute values. Okay. So quick reminder of what an absolute value is. When you have the absolute value of a number, these are the symbols that we use for it. The absolute value gives you the direction. I'm sorry, it gives you your distance, not your direction. So essentially take whatever's inside here and make it positive. Okay. So 1, 2, 3. -1, -2, -3. The absolute value is of -3 is 3 because we say, I don't care which direction I'm going, how many units away from 0 am I? I'm 3 units away from 0. The absolute value of 3 is also 3 because I don't care which direction I'm going, I just need to know how many units away from 0 I am. I'm 3 units away from 0. Okay, so the absolute value of 0.832 is 0.832. The absolute value of -0.947 is positive 0.947, right? To find the absolute value, you take the thing inside and just make it positive. If it's already positive, great. If it's not positive, make it positive. Okay, so now it's like we're comparing apples to apples rather than apples to oranges. So we look at these two and we say, okay, well, which of these two is closer to +1? This one is closer to +1, so this one has a stronger correlation than this one, right? -0.947 has a stronger correlation than +0.832 because it is closer to -1, or its absolute value is closer to +1. Okay, so correlation coefficient of -0.947 is a stronger correlation because its absolute value is greater than the absolute value of the other one. Okay. All right. So what does it mean to say correlation does not imply causation? List a pair of variables that have correlation but no cause and effect relationship. Okay, so I don't know if you guys know this about me, but my degree is not actually in math. My degree is in psychology. And if they drilled anything into our heads back when I was in college, in every single one of my psychology courses, was that correlation does not equal causation. Okay, hopefully you have heard that phrase before somewhere. Correlation does not equal causation. And they always gave this great example that I absolutely love. So they give this example of I'm going to do this here, the number of ice cream cones sold. Okay, like per day or per week or something. And they compared that to the murder rate. And what do you think they found? A super, super strong positive correlation, right? So we got all these dots that are super, super strongly correlated. If you draw a line of best fit, you are getting a correlation coefficient of almost exactly 1, right? Or R is approximately 1. Does that mean that the more ice cream we eat, the more we murder? Or does that mean that the more we murder, the more ice cream we eat? No, no, it does not. Correlation does not equal causation. Did I spell that right? Okay, correlation does not equal causation. I'm going to drill that into your heads too. No, the what's happening here is there's another factor that's playing into it. That is something that ties these two things together. This is not causing this, and this is not causing this. Okay, there could be a variety of things that make a super strong correlation coefficient. Okay, so one of them could be that there is some type of link. Okay, so in this case, the link was something to the effect of like, when it's hotter outside, violent crime increases. That's something that studies have shown, that generally the hotter it is outside, violent crime increases. Also, the hotter it is outside, the more likely we are to want to go have some ice cream. If it's 30 degrees outside Fahrenheit, I'm not going to get ice cream, but I am more likely to get it if it's, 90 degrees. Okay. So there's another factor here that is linking these things. This does not cause this, and this does not cause this. They are correlated because they have some other factor in common. So that might be something that happens. Now, another thing that might happen is that two things don't have anything in common whatsoever. And it really and truly is just complete coincidence that the two things are correlated. Okay. So I know a lot of people, they don't like statistics, and it's a difficult class or it's a boring class. But one of the things that I think is so important about taking statistics is that it makes you a better citizen. You are a more informed human being and citizen of this country and of this earth if you understand, and we talked about this a little bit, I think in the first or the second chapter about like misleading statistics, right? When you see these reports on whatever news station you're listening to, and they show these charts and these graphs, if you look at them, you might find some concerning things. Things that are like, yeah, that's misleading because of XYZ, the things that we talked about in the first couple chapters. Or you might look at something and say, wait, their sample size is like super small. That's not really useful at all. Why would they do that? Those numbers aren't going to mean anything because that sample size is so small. Or you might see things like this, where they put two things up against each other and say, oh look, there's this great correlation. Obviously, one of these causes the other. No, correlation does not equal causation. Okay, having said all that, let's go ahead and answer this question. What does it mean to say correlation does not imply causation? The fact that two variables are strongly correlated does not in itself imply a cause and effect relationship between the variables. Okay, and then the second part, it says, which of the following pairs of variables have correlation but no cause and effect relationship? So for this one, it is the number of school buses at the school and the number of teachers at the school. So kind of similar to this, where there's this other factor going on, that the more there's this third factor, right? So there's the more students you have at the school, the more likely you are to have more teachers, right? And the more students you have at the school, you're going to have more buses. But having more buses doesn't cause you to have more teachers. Having more teachers doesn't cause you to have more buses. Those things are correlated because there's this other factor that's linking them. Also, again, sometimes you do have that third factor that's linking them. Sometimes there is absolutely nothing linking them. There are all sorts of studies out there, and you can find graphs that have particular slopes of, of their data, and you can find another one that is just going to align almost exactly with, with their data points lining up. Doesn't mean they have anything to do with each other. Okay. All right, rant over. We are almost done here. Okay, so number 23, let me zoom in a little bit. I don't know, I feel like it's just so blurry. Okay, the scatter plot of a paired data set is shown. Determine whether there is and they've got some options here, okay? A perfect positive linear correlation, a strong positive linear correlation, a perfect negative linear correlation, a strong negative linear correlation, or no linear correlation between the variables. Okay, so let's talk about what each of those would look like. So if I have a perfect positive linear correlation, it means that every dot is exactly along the line of best fit, right? If I have a strong positive correlation, then they're not exact, but they're really close, right? So something like that. A perfect negative correlation would be, again, they're all straight in a line. A really strong negative correlation is, okay, they're not exact, but they're super, oops, putting too much pressure here. Super strong negative correlation. Okay. And then, and these are all linear, right? Linear meaning lines, right? We just drew a bunch of lines. The other option is no linear correlation. This does not create a line, right? This creates some sort of like a U shape. This kind of creates like I don't know if you guys remember like parabolas, right? Like an x to the second power. Not that you need to know that or anything, but just that is not a line. These are straight lines. That's not a line. So there is no linear correlation. Okay. All right. Okay. Find the equation of the regression line for the given data. Okay, so we talked about this a little bit before, right? That it gives us this a plus bx, but that's not the standard form of a line. The standard form of a line is the bx plus a, where the b is the slope of the line and the a is your y-intercept. Okay, so they're going to give you an A value and a B value, and you need to put them in the right order into the equation, right? I really should have my colored pens for this. Let me grab them real quick. Hold that thought. I'm going to get a drink and grab my colored pens. Okay. All right. So, and I'm dropping my pens. Let's try that again. Okay, so just like with the other ones, we are going to start by going into Stat, Edit, and we're going to plug these in to our lists. Your X is going to be your L1, and your Y is going to be your L2. I'm going to put mine into L5 and L6 just because, again, I already did so that I wouldn't have to spend time here. So I'm going to go Stat and Edit, and then over in L5 and L6, I have I have all these numbers. Okay, so now we're going to go to, we're going to go to stat, we're going to go over to tests, and we're going to go down to F, right? We can either scroll down or I'm going to scroll up because F is near the bottom, linear regression t-test. Now, if you've put it into L1 and L2, then you'll make sure that that says L1 and L2. I'm going to put mine as L5 and L6 because that's where mine are located. Frequency, you leave it at 1. Leave this alone. You can have that as Y1 if you want, and then calculate. Okay, so again, it's reminding us y equals a plus bx, and then it's giving us a, and it's giving us b. Now, you'll notice that these are really big numbers, right? They go for a lot of decimals. We don't need to give that many decimals. They're just rounding to like 3 decimals here, okay? So the a value that it gives us is let me write this in, well, yeah, negative 0.552 if I go to 3 decimals. And the b value, make sure you guys can see that, the b value that it gives us is 2.097 when I round. Okay, so this is my A, right? This is my A, and this is my B. This is my B. Okay, so I'm going to write y equals ax, I'm sorry, a plus bx. Sorry about that, a plus bx. All right, so I'm going to write my a. I'm not going to write my a. Sorry, this is not the order that we want it in. We want it in bx plus a. Getting ahead of myself here looking at stuff. All right, b. I want my b. b is 2.097. And then I write the letter x. And then I write my a, which is negative 0.552. Now you'll notice here I wrote a plus because there's a plus there. You can just write a negative because we are adding a negative number. So we have, sorry, the lights just got dim because nobody's moving out there because we're closed. So they're on a movement sensor. So sorry if it just got a little dark. We're almost done, guys. So if you add a negative number, that's the same as subtracting, right? That's why we have a negative here, okay? So I feel like a lot of times people confuse the order because it gives you the a plus bx, but just remember the bx has to go first. So whatever the b value is, that has to go first, okay? All right. Then we have 25. The data below are the temperatures on randomly chosen days during a summer class and the number of absences on those days. Find the equation of the regression line for the given data. Okay, so again, you're going to do your x's is always your L1, your y's is always your L2. In my case, I have L7 and L8. So again, you're going to go to Stat, Edit, and you're going to fill in into L1 and L2 or whichever lists you have. I have them in 7 and 8. And then you're going to go to Stat, Tests, and then go all the way down to F, Linear Regression T-Test, and plug in what you have. So I have to go L7 and L8. Leave everything else alone and calculate. So again, I'm being told that my A value is negative 30.267. Sorry, that would be 268, but they're just rounding to 2 decimals here. And my B value, I think my pencil just ran out of lead. Of course it did. like the second to last problem. Of course it's going to run out. And my other one is also out. Okay, 0 for 3. Okay, I'm going to have to replace the lead. Hold that thought. While you're waiting for me, you can definitely go try it on your own. All right, see if you get the right answer. Okay, there we go. All right, so my B value is, what is that, 0. Well, how many decimals? They want me to go to 3 decimals. So that's 0.449 if I round to 3 decimals. Okay, so we are being reminded that the equation is y equals a plus bx, but we don't want it to write it like that. We want to write the b term first. Okay, so we're going to do y hat equals b, 0.449, x plus the a term, which is negative 30.27, or if you don't like having to go back and erase your plus and your minus, just wait to put the sign until you see what the sign of your a value is. Okay? And that's how we're getting this right here. Okay. All right. Okay. Oh, okay. Not the second to last problem, but close. Okay. Given that the equation of a regression line is, and then they give us an equation, what is the best predicted value for y given that x equals 3.8? Assume that the variables x and y have a significant correlation. If they didn't have a significant correlation, then we couldn't do anything with this. All right, so again, thinking back to algebra, if you had an equation with x's and y's, you can plug in an x and solve to find the corresponding y, right? Like, do you guys remember making like a table of points? That's all we're doing here, right? They're giving us an x value of 3.8, and they're asking us to plug it into the equation to find the corresponding y, or in this case, y hat, right? So we have y hat equals negative 1.5x plus 1.2. And they're saying, hey, instead of x, use this value for x. Use 3.8. It's good standard practice when you're plugging in a number into a variable, you use parentheses. Really, this is just multiplication, right? So this is just something that I can plug into the calculator, right? So that's all we're going to do. We're going to say, I'm going to clear. I'm going to say negative 1.5 times 3.8 plus 1.2. And that's going to give me negative 4.5, right? My corresponding y value is negative 4.5. Well, if I go to 2 decimals, 0.50, right? So you're just plugging in the value to estimate what that y would be, right? We don't know what exactly it is, but that's the estimate, the best predicted value. Okay. All right, the data below are the temperatures on randomly chosen days during a summer class and the number of absences on those days. What's the best predicted value for y given x equals 81? And assume that they do have a significant correlation. Okay, so kind of the same thing as the last problem, but we have to do more work to get there first because they did not give us the equation. We have to come up with the equation ourselves. Once we come up with the equation, then we can plug that value into it, right? So again, we have to do, this goes in L1, this goes in L2. In my case, it's L9 and L10. So you go into Stat, Edit, fill in your values. The X's are all L1, the Y's are all L2, or in my case, 9 and 10. Let me just double check that that is what I have in that list. Yep. And then you're going to go to Stat, Tests, and you're going to arrow all the way down to F, Linear Regression T-Test. You're going to tell it which two lists to look at. Leave frequency as 1, leave that alone, and calculate. Okay, so it's reminding us y equals a plus bx, but we actually want bx plus a, right? The b value is 0.449x. I mean, the b value is just the 0.449. It's not the x. The x is being multiplied by b. And then our a value is a negative number, so I'm going to subtract or add a negative, 30.27, right? Because I think they've been going to 2 decimals there. Okay, so we have our equation, right? That's the equation. Now we can actually plug in the value that they've asked us to, an x value of 81. Okay, so we're going to plug in an 81 wherever we see x, and then we're going to solve for y or y hat, right? 0.449, and then instead of x, I'm going to write 81 minus 30.27. So I'm going to go 0.449 times 81 minus 30.27. And I get something really, really close to 6. So that's how they're getting 6. Okay. There is another way to do this that I'm not going to go through now because it takes too much time to talk about, like, how to get your calculator to do stuff and trace stuff. But if you want me to show you how to do that, you can email me later, and we can like set up a time where we can get on Teams, just the two of us, and I can show you how to do that. But we don't have time tonight. Sorry. We closed 20 minutes ago. Sorry. These are kind of inconvenient that they're at 3, because if they go long like this, then we're just like way over time. Okay, 28, explain how to predict y values using the equation of a regression line. That's what we've been doing, right? They just want us to explain what we've been doing for the last 2 problems. We substitute a value of x into the equation and solve for the corresponding y, right? Okay, we're almost there. In order to predict y values using the equation of regression line, what must be true about the correlation coefficient of the variables? It has to be significant, okay? So if there isn't a significant correlation, then we're not allowed to use that equation, right? When I say the equation, I mean the y hat equals bx plus a. We can't try to plug values in for x to predict y if the correlation coefficient for this says that they're not says that there is not a significant correlation, okay? Because like if you think about, like if you have stuff that's not really got a strong correlation, I mean, I could draw a line of best fit. Oh my gosh. My lead is stuck or something. I could draw a line of best fit, but my R value is going to be, I don't know, pretty low. Like, I mean, you can't really see all those little dots, but like I got dots kind of all over the place here. I don't have a very strong correlation. So my R is going to be kind of low, right? Closer to 0 than to 1. So I can't really use this line to predict anything because there's not a strong enough correlation, right? So that's what they're trying to get you to remember here. Okay. And yeah, this is the last one. All right. This is the last one for sure. Okay. So lots of things that they're having us do here. Find the equation of the regression line for the given data. Okay. So again, we're going to go into stat and edit, and we're going to plug all of those in. So let's see, I've got in my notes here, which, yeah, L11 and L12, but for you guys, it's going to be L1 and L2. For me, it's L11 and L12. So you go stat, edit, and you plug into whichever list you want. I have 11 and 12. Then you're going to go to Stat, Test. You're going to arrow all the way down to F. F is in Foxtrot, linear regression t-test. You're going to tell it which lists to look at. I'm telling it L11 and L12, and then calculate. And it is giving us an A value of 20.61 when rounded to 2 decimal places, and a B value of 0.041 when rounded to 3 decimal places. And you can see that it's actually reminded you already, hey, don't forget that it's AX. BX plus A, sorry, BX plus A. So they haven't told you those letters, but they're reminding you that the thing attached to the X has to go first. And this is telling you that the B is attached to the X. So if you ever get confused as to which one is supposed to be attached to the X, it tells you right here in your calculator. The B is attached to the X. So you don't have to memorize that if you're having trouble with it. Okay. Then they want us to choose the correct graph. Okay, so here's where some more of this comes into play. Okay, what we're going to do is we do want to graph this, right? So we're going to go to see up here where it says stat plot. Above the y equals, it says stat plot. We want to do a stat plot. So I'm going to do second y equals. Okay, and plot 1, I'm going to select. I need to make sure it says on. I need to make sure this first type is selected, and I need to make sure it's looking at the right lists. So I need to tell it L11 and L12. And then, so in order to actually graph this, so let me pull this back up here. We need to make sure that the plot is on. Then in order to actually graph it, we have to hit the zoom button and go to number 9, zoom stat. Okay? So there's no like enter. You have to go zoom button right up here at the top. And then you go down to number 9, which is zoom stat. Okay. And it's going to do that. All right. So it's given us the dots and it's given us the line. We have to select which of these graphs is on the calculator. Well, we can tell right off the bat that this is going in the wrong direction. This has a positive slope. That one had a negative slope. We don't have a negative slope. It's not B, it's not C. So now we're looking at A and D, okay? But what you'll notice here is that for A, I know this is really small, but for A, all of these dots are below the line. Well, that's not a line of best fit. The line of best fit goes through as many of the lines as possible. Technically the line of best fit, it has the least distance from the line to each point as possible. So it's not going to be on one side of a whole cluster. It's going to be going through that cluster. So it's not A, it's going to be D. Okay. All right. Now they want us to predict the value of Y for X equals 498. Okay, I know I said that I wasn't going to show you how to do this because of time, but I'm going to show you how to do this because it's just so much easier. So we can absolutely, for A and B and C and D, we can absolutely do what we did do on the last one where we have our equation, which, by the way, real quick, what's our equation? Our equation is the A value, hold on, stat test, linear regression t-test, calculate. Okay. Oh, shoot, wait, did I update? I did, okay. Oh, we already calculated that. I'm like, oh, what was our thing? It's right here. Yeah, I don't need to rewrite our equation. So we can absolutely just take this X value, plug it into this equation and find the corresponding Y, okay? Or we could have our calculator do it, right? So we're going to go back to Zoom and then number 9, which is Zoom Stat. Okay, now what we can do is we can hit this trace button right here, trace. If you hit trace, you notice some things pop up. Sorry, that reflection is kind of annoying. So if you use the up or the down buttons, what that's going to do is it's going to alternate between selecting your data points, like those individual points, and selecting the line itself, the line of best fit. So right now it's selected this data point right here. If I hit up, now it's going to be like, oh, okay, let me jump to the line. If I hit up or down, it's going to jump to another point. Like it's going to jump to the points rather than the line. So that's if I hit the up or down. If I hit the left or right, it's going to go, well, I can type in an X value. So, okay, let me hit the, I'm going to go onto the line. And then when I hit, oh, sorry, I'm looking at my notes and I'm like, what? That's not what I meant. What I meant to say was that if you're selecting the line, if I arrow to the left, I'm going down the line. I can go down to, kind of all of these in between numbers, right? But I can also try and calculate something, right? See how this says calc above the trace? So I'm going to say second trace, and I'm going to have it, I want to calculate a value, and I'm going to plug in an X value of 498 and hit enter. And it says, oh, well, when X is 498, Y is about 40.989465, which when rounded is approximately 41, right? So as long as I've selected the line and not the points, whoops, trace, let me hit trace again to get back onto it. So I don't want to be on the points, I want to be on the line. So I'm on the line, right? I'm tracing the line. Now I want to calculate, so I'm going to say second trace, and I'm going to calculate a value, and I'm going to plug in an X value of 645 this time. And it tells me, oh, your Y value is about 47. Okay, great. Okay, then, I mean, I know you guys can see the answer. We'll talk about what's going to happen here. So again, I want to make sure I'm on the line. So I say trace, I go make sure I'm on the line. So if I go left and right, I'm tracing. I want to calculate, so I'm going to do second trace, a value, and an X value of 310. And it says, whoa, hold up a minute. Attempted to use a variable or function where it is not valid, right? This is not valid because this is not meaningful. Now, why is this not meaningful? I just moved the thing away, but the reason that it is not meaningful is that if you look at your original data set, the lowest value here was what, 483? And the highest for the X's, the highest value was 772. So the lowest I can go is 483. The highest I can go is 772. If I try and go beyond that, like significantly beyond that, I just can't be sure that this pattern is going to hold up, right? All we know is what's happening from here to here. Maybe we can go a little bit beyond, but we can't go all the way down to 310. That's pushing it. That's way too far below the data that we've been given. We don't know that the pattern that we have here will hold up if we go beyond in either direction. Okay, so it's going to tell you, no, you can't do that. And you're going to say, oh, that's right, this number is too small. It's not meaningful. I can't make a meaningful assumption or a meaningful guess. What's the word I'm looking for? A meaningful estimate with a number that's so far outside of what we've been dealing with, right? Okay, and then the last one, predict the value for x equals 727. Just for the heck of it, let's do this one by hand. 0.041 x plus 20.61. So I'm going to plug in an x value of 727. going to say 0.041 times 727 plus 20.61, and I get about 50. All right. Okay. All right. Well, you made it all the way through. We're back at the beginning. So like I said, I will be sending out a link to this recording as soon as I can get it rendered. Sometimes it takes a really long time if the recording is really long, so please be patient. But I will get these out to you guys, and I will also be sure to send you this thing. And again, you can always reach out to me if you're having trouble understanding what the heck I have written here. um, but yeah, that's going to be it for today. Don't forget to, reach out to your instructor if you have questions. Reach out to, the physical academic support center site that's closest to you, or you can hop on the online virtual chat that's open later in the evenings than the ASCs are. And well, except for the building 115 in Daytona, that's open until 8 Monday through Thursday. And then also on Saturday, building 115 ASC is open. It's the only location that has Saturday. Right. Okay. Good luck.